Okay, this is shear, and this is example 5 continued, and this is hopefully going to be the final sheet. So we've got a poorly drawn eye section because it's being shown as being much thicker than it actually should be. And then we're going to be talking about this concept called shear flow. So that's going to be the neutral axis of the section. And as we know, there are going to be shear stresses flowing up the web, which are going to be resisting our shear force. So we will show the shear stresses not as stresses, but as a shear flow. And remembering that the relationship between shear stress and shear flow is that shear stress is equal to shear flow divided by thickness. So up the flange, or across the flange, there's going to be a shear flow going down to 0 at the end there, and that value there is going to be Q1 and Q2, and that value there is going to be Q1, and both are going to be of the same magnitude. So we've already seen that Q3, which is across there, so the stress Q3, which I'm going to draw here, and then so Q3 would be a bit larger, so Q3 is approximately equal to Q1 plus Q2. And that's the case for this thin walled assumption that we're making. And then it's going to go maximum at the center of the beam, where the which coincides with the neutral axis. And we can make similar arguments for the bottom part. So again, showing the arrows getting progressively smaller and smaller, and then this case here, for the reasons we said in the first sheet, the shear flow is going to be in the opposite direction. So it's called shear flow because it's analogous to the flow of fluid going through the section. So now we come to, well, let's draw that out here first as well. So that would also be the same value as Q1, and that would also be the same value as Q2 there, going up to a value of 0 at the 4 corners. And just to complete the picture, I'll draw that around there with that value there being Q3. So we're asked to calculate the value of Q4, So which would be that value there, that value Q4. So we should know by now that we are taking that we have to calculate it at the neutral axis. So we've got that section there, then coming down here. So we've come down here, and then I won't show the bottom half, but I'll just call that the neutral axis. So we have our thickness T. We have our distance down from the top, which would be big D, which would be the overall depth minus 2T, and that would be divided by 2, so that's going to be that distance there. We've got B as the breadth of the section, and then we would have T as the thickness of the flange, of the web. So let's deal with the shaded bit first. So Q4 is going to be equal to our shear force V times the second moment of area to the position where we are calculating it, and divided by I. So let's take the V over I out, and then let's deal with the shaded area first. So dealing with the shaded area first, it's going to be D minus 2 capital T over 2. That's going to be multiplied by the thickness of the bottom area of the web, and that needs to be multiplied by the distance of the centroid of the shaded area to the neutral axis of the composite section, and that's going to be D minus 2T all over 4. So we've got another bracket, D minus 2T all over 4. So onto that we need to add on something else, and that something else is going to be this new shaded area, because we need to add all the areas together above the neutral axis, because the cut is at the neutral axis, so everything above it, and we will end up with V over I for that one times B times T, and that needs to be multiplied by the distance from the neutral axis to that part there where the centroid of that section would be, and that is going to be big D minus big D over 2, D over 2 minus T, you've got that right down, D over 2, yep, minus T, and that would be added on let's just write that out again, D minus 2T over 2 plus T over 2, and that would be equal to D minus T over 2, since T over 2 is going to be half the half that distance there, t over 2. So we've got d minus t over 2, and actually you should remember that we've done that bit before, and that value actually was q3, so we could cross that out, and instead of saying plus that bit here, we could say plus q3, which we have already calculated. So that's just to show that q4 can be obtained by adding on to the first shaded area onto q3, and then that would give you the maximum value. So that would be the max value of the shear flow. And remembering that the shear stress is equal to the shear flow divided by T, or the shear flow is going to be equal to the shear stress multiplied by T. So that shows the distribution of shear flow through the section, and then to turn that into the shear stress, you would then divide that by the thickness of whichever section of whichever member you're considering. So for the flange, you would divide it by small t. Sorry, for the web you would divide it by small t, and then for the flange you would divide it by big T to give the value of the shear stress.